Formal charge is a way to determine the correct Lewis structure if you can draw more than one. Let's look at this example down here below. So how you determine which of these two Lewis structures is the most correct is you're going to go through and you're going to count how many valence electrons, and you're going to subtract the assigned electrons. So every single atom will have individual electrons around it, perhaps, and they all will have bonds. When you look at a bond, you divide the bond between the two atoms that it's bonded. So remember, one bond is 2 electrons, so you will give 1 electron to each of the 2 atoms in the bond. So let's look at this first one. So my first oxygen here, I am going to look on the periodic table and find out how many valence electrons, and I find that I have 6 valence electrons. And then when I sign the dots, I can count them. 1, 2, 3, 4 are assigned right to the oxygen, and I split these bonds in half. So 5, 6. So 6 electrons there, and when I subtract, I get a formal charge of 0. Let's look at the carbon. So the carbon, I just have the 2 bonds on either side. So half of each bond goes to the carbon. So 1, 2, 3, 4. So 4 valence electrons minus the 4 that are assigned, I have a 0 formal charge. And then the second oxygen is going to be just identical to the first. So 6 valence electrons minus 6, I get 0. So the closer you are to 0, the better. So that's kind of the goal with this formal charge. So this one looks like a pretty good candidate as being the correct structure, the correct Lewis structure, because everything has a formal charge of 0. But let's look at this other one. So this other one has a single bond and then a triple bond, and let's do the same thing. So the valence electrons are going to be the same, 6 for each of the oxygens and 4 for the carbon. And let's count on that first oxygen how many electrons are assigned. So I have 1, 2, 3, 4, 5, 6, and then half this bond would be 7. So 6 minus 7, I do get a -1 on this side. And then for the carbon, cut those bonds in half, and I can count 1, 2, 3, 4, and 4 minus 4 is 0. And then on this second oxygen, it only has 2 of its own electrons, and the rest are in the bond. So 1, 2, 3, 4, 5. So 6 minus 5, I get a +1. Notice that when you add your formal charges, they should equal the charge on the molecule. And because it's neutral, then this should be 0 when you add them up. So notice all the formal charges of both of the molecules I did, they do equal 0, which is the charge of CO2 because it's a neutral molecule. As far as which one is most correct, it would not be this one. And the reason why is because 3 zeros are better than a -1 and a +1. Also, oxygens are very electronegative, and you wouldn't assign a +1 to a very electronegative element. All right, let's do another one. Draw the 3 possible Lewis dot diagrams for SCN-. So on this, I know carbon has 4 bonds, so I am going to just split them between the 2 here. And let's make sure we have all our dots. So we have sulfur has 6 valence electrons, carbon has 4, nitrogen has 5, and then this little minus means I have 1 more. So that totals, what, 12, 16. So I need to have 16 electrons. I have 8 so far. So let's give everything their octet. And I do have 16 around there. 8 plus 8, 16. Okay. Let's figure out a different way to draw this. So I'm going to do a single bond on this side and a triple bond on this side. And then just make sure there's an octet on that. And then on this other one, I'm going to do a triple bond on this side and a single bond on this side. All right, so now that I got them drawn and every carbon has 4 bonds and everything has 8, I want to just use the valence electrons to figure out which one is the most correct. So I'm going to start out with figuring out those valence electrons, and then of course figuring out the formal charge is our objective. So we have sulfur is in the carbon or the oxygen family. It has 6 valence electrons. Carbon has 4 and nitrogen has 5, and they're all going to have that. So I'm just going to go ahead and assign all those valence electrons. And then I'm going to subtract what's assigned. So on this first one, I have 1, 2, 3, 4, 5, 6. So that's going to give me a formal charge of 0. Carbon's going to have 1, 2, 3, 4, 0. And then this nitrogen, I'm going to have 1, 2, 3, 4, 5, 6. So I do end up with a -1. 0 plus 0 and a -1. And that does make sense because this is an ion. And I goofed and didn't put my brackets around all of these because it's wrong if you don't include the brackets. So let's do this lower left-hand one here. So the assigned electrons on the sulfur on this one would be 1, 2, 3, 4, 5, 6, 7. So a -1 there. Carbon, this one has 4, so half of each of those bonds. And then this nitrogen has 1, 2, 3, 4, 5. Okay, and they do total up a -1. And then we have this last one, sulfur. This one has 1, 2, 3, 4, 5. So subtracting that, I do get a +1. And then this carbon has 4. And this nitrogen has 1, 2, 3, 4, 5, 6, 7. So subtract it. And that does add up. So a -2 and a +1, I do get a -1. So let's evaluate each of these structures based on the formal charge. Right away I can see one that it's not going to be. And it's not going to be this last one. Do you see how they're farther away from 0 than the other ones? I have a 1 and I have a -2. So I know for sure that it's not going to be this last one. So I can eliminate that. Now let's look at the other two. So the other two I'm looking at, they have the zeros and they have a -1. So I have a -1 on a nitrogen. I have a -1 on a sulfur. So on this, you always want to assign the charge on the most electronegative element. So looking on the periodic table, fluorine is the most electronegative, and I have nitrogen and I have sulfur. Sulfur's a bigger atom. Nitrogen is going to be a little bit more electronegative. And so we are going to have this first one be the Lewis dot structure. So with that double bond. And sometimes it ends up being the single and the triple bond. It just kind of depends. So formal charge again is a way to determine which one is the most correct. And you want those formal charges to add up to equal the charge of the atom. And every single atom gets a formal charge. And you want each of those formal charges to be as close to 0 as possible. So in this one, when I'm trying to determine if the sulfur gets the -1 or the nitrogen gets the -1, you again assign the charge on the most electronegative element. All right, let's look at this example. So we have SO2. So I'm going to look at the formal charge just to see if this is a valid Lewis structure. So 2 oxygens and a sulfur. And again, here's my valence electrons. They each have 6. And then they're assigned electrons. This first one is going to have 6. And the other oxygen just looks like it. And then the sulfur has 2 of its own, and then sharing each of those, it also has 6. So we'll look at that. It's a 0. So that looks pretty good. That's what we want. We want to have all zeros. You can draw this structure like this with a single and a double bond. Let's look at this one and just kind of compare it. So again, they all have 6 valence electrons. Let's assign the electrons for that first oxygen. So it has 6 of its own plus 1. We get a 7. So we get a -1. This sulfur has 1, 2, 3, 4, 5 assigned to it. So that's a +1. And then this oxygen has 4 of its own, 6. So you can see that this one's the least desired because it is deviating from the 0. So it would not be this one. Okay, so, and that's a little weird because if I drew this one, this would give it 8 around that sulfur. So this is one of those exceptions where you have an expanded octet is most desired. So this would be the more likely structure. So let's do another one. So this one is CO2, which is the most likely structure. So we can go through and we can assign valence electrons to all of these. And then we can count the electrons that are assigned to it. Remember, in a bond, it only gets half that bond. So this one is giving some dots, so I'd only do half the dots. So this first one has 2, 4, 6, 7, and this oxygen has 1, 2, 3, 4, and this carbon has 1, 2, 3, 4, 5. So subtracting this, I get a -1, a 2, and a -1. And it is neutral, so those do cancel out. Let's do our next one. 2, 4, 6, 7, 1, 2, 3, 4 on this one, and 1, 2, 3, 4, 5. So subtracting this, I get a -1 and a +1. So that one's looking better. And this one has 4 on that first oxygen plus 2 in the bond, so 6. So that looks good. Oxygen 1, 2, 3, only 4. So I get a +2. And this last one, 1, 2, 3, 4, 5, 6, I get a -2. So that one doesn't look very good either. Now let's come to the last one. The first oxygen, I have 4, 5, 6. That carbon, I have 4. And the last oxygen, I also have 6. So that is the structure we're going to have. So again, formal charge just clears up which is the most likely. There are lots of exceptions to the octet rule. So always try to draw the octet rule, but just know that there's probably more exceptions than there are examples of the octet rule, especially if you have an atom that's really, really small, like boron or beryllium. You can have expanded octets, especially if xenon, one of the noble gases, is involved. And so just watch out for those. And I don't think you should ever see any odd number electrons, but just know that they're out there. This is an NO2 molecule. It is a neutral molecule, and we do have some resonance here, but it only has 1 electron on it that's not paired up, and that's called a free radical. I don't think that you should see that on your AP test. It's not something I would assign either. This is more of a complex problem. It's more explained in molecular orbital theory, which is a second-year college chemistry course.